So we are going to make the calculation of the potential produced by a disk. So we have a distribution of charge that is a Q, is uniformly distributed over a disk of radius A, R equal A, and we want to find the potential at the point P. What equation we will use? This equation. Why this equation? Because the disk is a finite object, and we can use it. So the potential will be K by ddq. So the small potential produced. So we divide the ring, the disk, into small rings like this one. So every one of these will have a charge ddq, and every one of these will produce a small potential at the point P. And what will be the potential, the small potential produced by ddq, by the small ring? Well, it will be K by ddq divided by the distance from the charge to the point of observation. But the distance from the charge, or the charge from the point of observation, is a square root of x0 squared plus a squared. Okay, is this distance, this distance, this is x0, and this is r square, okay? And the radius of the disk will be r. And I'm going to vary the radius r from 0 to a. So I need a DDR in the equation. So to find the DDR, I would say that ddq is sigma by dd area. But the area of this onion ring is 2 pi r by ddr. So I will plug in ddq here, and I will have that ddv is k sigma k ddq, that is sigma by the area divided by this. So I will put it these are constants. This is not a constant now because it depends of r. So this equation will say that k by 2 pi r by the integral from r equals 0 to r equal a of r that multiply x0 squared plus r squared minus 1/2, and the integral ddr, and the integral of this will be this function x0 squared plus r, because if I make the derivative of this, I will find this. Let's go to do the derivative. 1/2. If you do the derivative of the function, you will say 1/2 x0 squared plus r squared to the power minus 1/2 by 2r. The 2 will go, and the minus sign, so the integral is this one with the minus sign. No, there is no minus sign. It's correct. So this is the integral. So you can plug in b of p for the point k sigma 2 pi x0 squared plus a squared 1/2 minus x0 squared square root. So from r equals 0. And this is the solution of the potential. And what is for this? So you have v of x. Okay, what? Why do we use this? You have v of x like this. Let me put instead of x0 now x plus a squared to the power 1/2 minus x. You have this potential. And what? Well, you have the electrical field. E of x is minus the derivative of v respect to x. You make the derivative of v respect to x, and you will find the electrical field. You go to the previous, to the chapter 21, you see the result, and you will see that making the derivative of v respect to the x of this, you will find the component x of the electrical field. Let's go to do it, maybe to remember. K sigma 2 pi, the derivative of this will be 1/2 squared, x squared plus a squared by 2x minus 1. Yes? So try to find, if I didn't make any mistake, this is the component x of the electrical field produced by a disk of charge. And this is the potential produced by the disk of charge. So from the potential, I find the electrical field. And why we use the potential? Because it's easy to find the electrical field from the potential than to find the electrical field directly without not using the potential. Okay, that's all.